Hello everyone, welcome to Algo-holic, the place where you learn not just the solutions but the thought process behind solving problems. Today we're solving the problem remove duplicates from sorted array. We're given an integer array nums which is sorted in non-decreasing order. We're supposed to remove the duplicates in place and the order of the final array matters. In the end, we're supposed to return the number of unique elements in the array. Let's look at an example. The array has 1, 1 and 2. We remove one of the ones, so the final array is going to be just 1 and 2. Since there are two unique elements, we return 2. So it's a straightforward question. There's a blank in the end, which tells us that the testing algorithm is not going to look at that part of your array. So that is what this code tells. So what is the brute force way of solving this problem? Let's say we have an array 1, 1, 2, 2, 2, 3. So let's run a loop. The pointer is at the first index. Now we need to check if 1 is repeated. Now, how can you check that? We can run a linear search, but since we already know that the array is sorted, we don't have to run a linear search. We just have to check if the next element is equal to 1 or not. If it is equal to 1, we just pop it out of the array. So since here it's equal to 1, we just pop it out of the array. Now, what happens when you pop an element from a middle of the array? Every element to the right of it needs to be copied to the left of it so that we can still access that particular index. So the time complexity of every pop is going to be O of n. And if the array has all ones, for example, 1, 1, 1, that's going to be O of n into O of n, which is big O of n squared. Now, this is a valid solution, but it is not an efficient solution. Now, how do you go about optimizing the solution? Now, there is another solution that we could have come up with if the question did not ask us to solve the problem in place. Since we only care about the unique elements in the list, why not just convert the list into a set and return it? This can be done, but there's a problem here because we lose the relative order of the data. But we can also go around that by sorting this, because since we know that the question is in a sorted order, the answer is also going to be sorted. So we can just sort the set and we return the length of the set. This is a valid solution. The time complexity of this is going to be big O of n, as it takes n time for converting from a list to a set, and sorting is going to take n log n. So the final time complexity is going to be n log n, and space is going to be big O of n. But this is not a valid solution because the question explicitly asks us to solve the problem in place. Now let's look at the brute force solution again. Since we were popping each and every element like this, that is what was adding to our time complexity. Now, can we somehow remove that? Can we maybe use a two-pointer approach to remove that, or can we use the last part of the array to remove that? Let's look at how that can be done. 1, 1, 2, 2, 2, 3. Let's initialize two pointers, slow and fast. Both are pointing at the first value. Now, all we need to do is check if the current value equals the previous value, because we know that in a sorted array, all the repeated elements are found together. So we don't have to perform a linear search every time we are finding a value. So we take the current value and we check if the current value equals the previous value. There is no previous value, so we move both the pointers. Now we again do the same operation where we check if the current value equals the previous value. Now 1 does equal 1. What do we do here? We keep the slow pointer over here and we only move the fast pointer. Now, why do we do this? We do this because we know that 1 is repeated and 1 needs to be replaced. So the slow pointer points towards the index which needs to be replaced, and the fast pointer looks for another unique value to replace it with. Now we check if 2 equals 1. 2 does not equals 1. So we take the 2 and we put it at the slow pointer's index. Now the array is 1, 2, 2, 2, 2, 3. The slow pointer was over here and the fast pointer was over here. Since we just did the replacing, we can move both the pointers. Slow pointer comes over here and the fast pointer comes over here. Now we check if 2 equals 2. 2 does equals 2, so we just move the fast pointer. Now we again check if 2 equals 2. 2 does equals 2, so we again move the fast pointer. Now we check if 3 equals 2. 3 does not equals 2, so we take 3 and we put it at the slow pointer's index. So the array is going to be 1, 2, 3, and these values are not going to change. So this is the final array. We've reached the final part of the problem once the fast pointer goes out of bounds. So the slow pointer is pointing at 3. So we just return this part of the array. This is also going to be returned, but since we are returning 3, which signifies the number of unique elements, the testing algorithm is not going to look at this part of the array. So this part of the array is what matters. What is the time complexity of this? We just move both the pointers from left to right. So that's just going to be O of n, and we're not taking any extra space. So this is the most efficient solution. Let's quickly code up the brute force solution. So index is 0 while index is less than the length of nums. Now we're checking if the current value exists in the right side of the array. So while nums index, which is the current value, in nums index plus 1, which is the right side of the array. If it does exist, we just need to pop it out. So nums pop index plus 1. Outside this loop is where we increment index. Return the length of nums. This should be it. Yep, this works. So let's look at the solution which uses set. So let's say unique elements is set of list. So we're just converting the list into a set and we're sorting it. Now we just need to put it back to the same memory. So nums equals unique elements and return the length of nums. Yep, this works too. Now let's look at the most optimal solution. We initialize 2 pointers, slow and fast. So slow is 0, and we can just use fast in the for loop. Now we're checking, let's just start with 1 actually, so that we don't have to handle the edge case. So we're checking if the current value equals the previous value. So if nums fast is not equals to nums fast minus 1. So we're checking if the current value equals the previous value. If it does not equal the previous value, we replace it. And we also need to increment the slow pointer. Outside here, we don't have to increment the fast pointer because it's already in the for loop. So this is it. We just need to return the length of, we need to return the slow pointer because slow pointer is going to be pointing at the last unique element. Yep, it works. Let's just run to make sure it's efficient. Yep, it's efficient. C++ code looks pretty much the same, where we have the slow pointer initialized at 1, the fast pointer also initialized at 1. We're checking if the current value equals the previous value. If it doesn't, we are making the change, and in the end, we're returning the slow pointer. Java code looks pretty much the same, slow pointer at 1, fast pointer is also at 1. We're checking if the current value equals the previous value and returning the slow pointer. So that's all for today. I hope you found this video helpful. Your feedback helps me make better content. So please share your thoughts in the comments below. I'll see you in the next one.